Magnetic force on a point charge. Magnetic fields. Magnetic fields are similar to electric and gravitational fields. They are symbolized by B, and they are vector quantities. Magnetic fields are produced by the motion of electric charges. The direction is given by the direction of a north pole of a compass needle pointing towards that location. Magnetic field lines can be used to show how the field lines, such as traced out by a compass, would look. A charged particle in a static, not changing with time magnetic field will experience a magnetic force if and if only the particle is moving. A particle at rest, sitting in a magnetic force, will have no force acting on it. So if a charge Q with a velocity v moves within a magnetic field and v makes an angle Q with respect to b, then the magnitude of the force on the charge is F equals v QVB sine of Q. Or if they are perpendicular to each other, then it will be QV perpendicular B. Basically, the idea is if the B field is going this way and the charged particle is moving, then maximum force would be when the B field and velocity are at 90 degrees to each other. As you decrease the angle between the V and the B, the force becomes QVB sine of theta, if theta is the angle. Or if the Q is moving in the direction of the P field, the charge will experience no force at all. So the magnitude of B field is defined by measuring the force on a moving charge. So B is by definition force divided by Q, the charge, V sine theta. The SI unit of magnetic field is Tesla, often represented as capital T. 1 Tesla is 1 Newton per Coulomb meters per second, or 1 Newton per ampere meter. Earlier non-SI unit of B, but sometimes still in use, is called the Gauss. The Earth's magnetic field is about 0.5 Gauss. Now here's where the notation becomes very, very important. To depict a vector oriented perpendicular to the field, we use crosses and dots. A dot indicates a vector going into the page. Think of the tail of feathers of an arrow disappearing into the page. A dot indicates a vector coming out of the page. Think of a tip of an arrow coming towards you out of the page. So a B field pointing towards you will be represented by this dots. And a B field going away from you or into the page will be represented by these crosses. So in order to determine the direction of the force, you will need to use what we call the right-hand rule. So a positively charged particle in a magnetic field, so note what this is. This is a field that is going into the page, right? And a velocity vector that's going towards the right side. What will the force be? So we will use what is called a right-hand rule. What is a right-hand rule in order to figure out what the force is? The right-hand rule says if you cross the fingers from the direction of V towards B, it will tell you the direction of the force, just like this. So in this case, it's going to be this way, the velocity vector is that way, and the B field is going into the page. How do I draw it into the page? Like this. So my B field is going that way. What is the direction of the force? Going up. That is for a positive charge. Now for a negative charge, what you need to do is put a minus sign with the force, so the force will be going downwards. Let's look at this example again. Right-hand rule is given by this. F equals Q V cross B, where Q is the charge, V is the velocity, and B is the field. So let's look at it. Let's look at an example on the board. So imagine that this is your B field going into the page. And you have a positive charge, positive Q, that is going towards the right. Okay? So the B field is into the page. I can do this also. So I have a right hand, my index finger points, and then I'm going to point it towards the towards where the B field is. So my charge is here, it points towards that way. So my index finger or my hand shows that my Q direction is this one, right? Now, what is my B field doing? So I can flip this over like this to show you where the direction of Q is. Now I rotate my fingers towards the direction of the B field, goes up, my thumb goes up, this is the direction of the field, right? So my field goes upward. Note, Q, V, and B are all at 90 degrees to each other. So this is kind of where it becomes very interesting. It's actually a three-dimensional plane. On the other hand, what if in my field, same V, my field is coming out of the page? Okay, what will it look like? My direction is still outwards, but in this case, my B field is pointing outwards. So what's the direction of my force? My force will be given by the direction of my thumb, which is downwards. So for a positive charge going this way with velocity, the direction of the force will be downwards, if the field is coming out of the page. Now let's do an example. Cosmic rays are charged particles moving towards the Earth, but at high speeds. The origin of particles is not fully understood, but the explosions of supernova may produce significant fractions of them. About 7/8 of the particles are protons that move towards the Earth with an average speed of about 2/3 the speed of light. Suppose that a proton is moving straight down directly towards the equator. What is the direction of the magnetic force on the proton due to the Earth's magnetic field? Explain how the Earth's magnetic field shields us from bombardment by cosmic rays, and where on the Earth's surface is this shielding effect least? So first of all, it says that the direction, what do we have to find? It says cosmic rays average speed is about 2/3 the speed of light. Okay? Then it asks me, what is the direction of the magnetic force on protons due to the Earth's magnetic field? So first of all, let's suppose this is my Earth, this is the North Pole, this is the South Pole. The direction of the magnetic field is going to be opposite. Remember we talked about this? This is going to be opposite to the direction of the magnetic north and the geographical north. So the magnetic north is this one. So the B field will go from south to north. Okay? And what it's saying is that the particle, the proton, is coming inwards. So VB goes this way. So now we have a B field that's pointing upwards and V field that's going in. Now it's asking me, what will the force be? So I know force is equals to QV times B, right? Okay, so Q is a proton, so it is a positive charge. V is towards the Earth. B is upwards. So where will FB be? So V goes this way, B goes up. So what direction is my thumb pointing? So V is this one, B goes up, and the direction of my my force will be into the page. And that I found from the right-hand rule. If we think about F is into the page from the right-hand rule, what this means is that this proton will actually be traveling towards the poles or towards the east in our map, and that's why we see those aurora borealis up in the north. Okay? Now the next question is, where on the surface is this shielding least effective? Well, the least effective will actually be at the poles themselves. Anywhere else, these particles will be deflected upwards to go towards these points, but if there was a particle coming in here or here, that's where the least shielding will occur. Example 2. At a certain place, Earth's magnetic field has a magnitude of 0.5 millitesla. The field direction is 70 degrees below the horizontal. Its horizontal components point due north. Find the magnetic force on an oxygen moving due east at 250 meters per second. Compare the magnitude of the magnetic force with the iron's weight, 5.2 times 10 to the minus 25 newtons, and to the electrical force on it due to the Earth's fair weather electric field, 115 newtons per coulomb downwards. Okay, so now bear with me here. This is going to be very interesting. It's not very hard, but it's very hard to draw this in on a flat surface. So what the question is saying is that the Earth's magnetic field, or B for the Earth, is 0.50 millitesla, and it is directed 70 degrees below horizontal. Okay? And it's saying that its horizontal component points due north. Okay? So now I'm going to draw something. So when we look at a map, even though on my picture I've been drawing north, south, east, west, this way, but when you actually look at the map, what it's doing is north, south, east, west. They are all directions in a plane where we can walk on, right? And then there's up and down. So what I'm going to do is on this surface, I am going to make the Earth's magnetic field be this way. Okay? So think of this as a three-dimensional space. This is north, this is south, this is up, this is down, and this is east and west. Okay? So right now, let's not concern ourselves about east and west too much. But what it's saying is that if this is horizontal, where will the direction of the magnetic field be? So this is up and down. So think about it. This is where the birds are, and this is where the ocean is. Okay? So the Earth's magnetic field, it says it points 70 degrees below the horizontal in such a way that its horizontal component, BEX, points north. Get it? So this is where the direction of the B field is. Okay? Then it says that an oxygen ion is moving east. So if this is north, this is south, this is east, and this is west. So this little oxygen molecule is moving towards east. Okay? Then it says, find the force on the oxygen moving east at 250 meters per second. So the force will be equals to QV times B. Okay? Which is now going to be 1.6 times 10 to the minus 19, because it is an oxygen, times 250 times 5 times 10 to the minus 4 Tesla, times what? Because this is a cross product, the way we replace the cross product is with sine of theta. Yes? What is theta? Now this is moving east. This is moving north and south. There is no field component along the east and west. There is a B field component along north and south, right? So basically, the theta, as far as we can tell, is going to be 90 degrees, okay? And sine of theta is 1. So this whole term becomes equals to 1. And when we calculate the magnitude, it is going to come out to be 2 times 10 to the minus 20. Now part B. In part B, it says we have to find the electrical force. We know electrical force is given by QE. Q again is 1.6 times 10 to the minus 19, and E is 150 newtons per coulomb downwards. I calculate that and I get 2.4 times 10 to the minus 17 newtons. Now, compare this to this. What do you see? You see that the magnetic force is much stronger on the iron than the gravitational force, right? Which is very, very tiny. However, the electrical force is much, much bigger than the gravitational force that's on the charged particle. So what have we learned so far? So for an electric field, the source for an electric field are charges. For a magnetic field, the source is moving charges. Electric field acts on charges. Magnetic field acts on moving charges. Magnitude of electric field is QE, and for the magnetic field, QVB sine theta. The direction for an electric field is parallel to the electrical field, whereas the direction for the acting of magnetic field is perpendicular to the B field.